In this video, we are going to discuss the t-test. In the last video, we discussed the z-test for the Portland cement formulation problem. We are going to use the same problem to continue the discussion of the t-test. Now, the z-test which we described, that would work perfectly if we knew the two population variances and they were given to us in the last problem, right? But what happens when the two population variances are not known to us? And in most cases, uh, that's the that's the situation where we don't know the true population variances. We can estimate the population variances from sample variances, but we don't know the actual real population variances. So z-test would not work in those situations. uh, since we usually don't know the true population variances, what would happen if we just plugged in the sample variances instead of population variances? The answer to that question is, if your sample sizes were large enough, say your sample size is more than 30 or 40, then z-test would still work just fine. It is a good large sample test for the differences in means. In our problem of Portland cement formulation, our sample size is 10. So if we don't know the population variance, our sample size is also not large enough. So z-test wouldn't work. But many times, like in our case, that isn't possible. As Gossett wrote in 1908. But what if the sample size is small? Then what can we do about it? It turns out that if the sample size is small, we can no longer use the standard normal distribution, the z-test, as the reference distribution for our test. Okay, so that's when we need to perform the t-test. So how the two sample t-test works? So let's see. We take the sample variance s1 square and s2 square for two samples to estimate the population variances sigma 1 square and sigma 2 square. The previous ratio, z0 ratio, that is basically we are talking about this ratio, y1 bar minus y2 bar divided by sigma 1 square will be replaced by s1 square, sigma 2 square will be replaced by s2 square. So that ratio will become this, y1 bar minus y2 bar divided by square root of s1 square divided by n1 plus s2 square divided by n2. However, we have a case where sigma 1 square is equal to sigma 2 square is equal to square. What we mean by that is the population variances of two groups, the modified formulation and unmodified formulation, they are same. So in that case, we can use the we can pool the individual sample variances in this formula here. Sp square pooled sample variance is equal to, given by this formula, n minus 1 times s1 square plus n2 minus 1 times s2 square divided by n1 plus n2 minus 2. And we know n1 is the sample size, we know s1 square, s2 square, that we can calculate from our samples. And the t-test becomes, so we are going to replace s1 square by sp square and s2 square by sp square, simplify it further, and then the t-test becomes, this becomes the simplified formula. T0 is equal to y1 bar minus y2 bar divided by sp times square root of 1 over n1 plus 1 over n2. So very good. It's like a very in line with the z0 formula we have, right? Now let's try to understand how to interpret this formula. Values of T0 that are near zero, that means there are y1 bar, the sample average for the first group versus sample average second group. If that is zero, the numerator is zero, that means the value of T0 will be zero. Values of T0 that are near zero are consistent with null hypothesis. That means y1 bar is equal to y2 bar, or mu1 is equal to mu2. That means the null hypothesis is true. there are no significant differences. That uh, in that will be true if t0 is 0. Values of t0 that are very different from 0, away from further they are from 0, they are consistent with the alternative hypothesis. That means the two means are not equal. In a way, t0 is a distance measure. We're measuring a distance between y1 bar and y2 bar, or mu1 and mu2. How far apart the averages are expressed in standard deviation units, because we are dividing by the standard deviation. So we are expressing the distance between y1 bar and y2 bar, or mu1 bar and mu2, in terms of how many standard deviation units they are farther away from each other. Another way to look at it is, this is our signal, right? Signal means the difference between mu1 and mu2 is the signal, and this is the noise, the standard deviation. So it is kind of signal to noise ratio. So for our problem, we can plug in the values of s1 square, s2 square, which we have previously calculated. You will see uh, s1 square, s2 square. We have all those y1 bar, y2 bar. We have all those values. So we plug in this formula here for sp square. That gives us the pooled sample variance 0.081. We take a square root of that to the to calculate the standard deviation. So that's 0.284. Then we plug in that sp value in the t0 formula. We know y1 bar, y2 bar. We know sp now. We just calculated. We know the sample size n1 and n2, and that will give us the t0 value minus 2.2. Now that means the two sample means are little over two standard deviations apart, right? Now the question is this a large difference? Is this a large difference? Now based on this value, can we reject null hypothesis? So we need to compare, just like when we calculated the z0 value, then we compared that with the using z distribution table. We compared that with the z reference z value. We use the alpha significance level of 0.05 or 5%, two-tailed test. Exactly same idea we have to use here, except now we will look at the t distribution, not the z distribution. So Mr. Gossett, he basically developed the t-test, right, in 1908. So, and we are going to use that now. So here is similar to our z distribution. This is the t distribution. Okay, we have the t distribution with 18 degrees of freedom. Now, where the 18 came from? The degrees of freedom is basically n1 plus n2 minus 2. So we know n1, we know n2, 10 plus 10, 20, minus 2 is 18. So that's why 18 degrees of freedom. With the critical region, two-tailed test, plus or minus t at 0.025 and 18 degrees of freedom. Now, what does 0.025 mean? Once again, alpha significance level of 0.05 or 5%, and that is divided in two tails, right? So 2.5% here, 2.5% here, 0.025, 0.025. uh, so we want to find out what is the t value here and here. Of course, on one side it will be minus, other side will be positive, right? And then we can compare that t value, our t value, calculated t value, with that t value. If our t value is farther than the t reference value in both ways, right? That means our we are going into the point 0.025 tail. So that means in this case it's very rare, right? It's very rare if the two means are uh, if the two means are unequal. So basically we are saying that if t0 minus 2.2 uh, is way into the tail, that's why null hypothesis should be rejected. If the value of t0 in this area is common, value of this t0 in this area is not common, right? And our reference t value is at that 0.025 is minus 2.101 and plus 2.101, and our value is minus 2.2, so it's definitely beyond the t reference value. So we need an objective basis for deciding how large the test statistics t0 really is. Is large, right? In 1908, Mr. W.S. Gossett derived the reference distribution for t0 called the t distribution. Those tables are at the back of your book. So if you look at the appendix of your book, you have the this cumulative standard normal distribution tables, and then we have table 2, the t distribution tables. And in this table you will see we want to find out that minus 2.101, right? Here is the screenshot of the table. So if you look at then we want the degrees of freedom is on this column here. 18 degrees of freedom we have, n1 plus n2 minus 2. So that is the row we need to look at. Okay, and we need to look at 0.025 alpha by 2 value, so which is 0.025 alpha by 2 value. So the intersection of these two is here. Intersection of these two, 0.025 is 2.101, and that's why we have 2.101 here and minus 2.101 there. Those are the reference t values. A value of t0 between minus 2.101 and 2.101 is consistent with equality of means. If our t value, calculate t value, is between these two values, then it is consistent with equality of means. It is possible for means to be equal and t0 to exceed either this or this, but that would be a rare event. And that's what happened here, right? A rare event that leads us to conclude that the two means are different. Okay, so that is one way to look at the problem. Second way is, instead of trying to compare t value with the reference t value, we take our t value here minus 2.2 and see how much area is beyond our t value. And same thing here on this side, right? How much area is beyond minus 2.2, and compare that area with the 5% significance level. If that area is less than 5%, less than 0.05, we come to the same conclusion. Okay, so we can calculate p value. So let's see. Uh, we can do it multiple ways. We can do it using tables. So or we can do it using a computer or Excel spreadsheet or any other statistical software. So let's first try to use the tables. Okay, our t table only gives probabilities greater than positive values of t. Our only one side, positive side tables. So take the absolute value of t0 here, minus 2.2, absolute value is 2.2. And now with 18 degrees of freedom, we need to find the values of t in the table that brackets this value, right? I mean, we may not exactly find 2.2, but we should find value like the values of t that brackets these. So let's look at this t table. So we need to look at 18 degrees of freedom. So you will see that uh, our t value, which is 2.2, is between, you will see here, is between 2.101 and 2.552. It's between, somewhere between these two. That means the area in the tail is between 0.025 and zero point zero 0.01, somewhere between those two values, right? So that's what is actually being explained here. So those values are 2.101 and 2.552. Our t value falls between those two values. Then the right tail, because the tables provided are only right tail, so the right tail probability for t for this 2.101 is 0.025, and for 2.552 is 0.01. But we need to double this because our we look at the two-sided t-test, right? So if we double 0.025, that would be 0.05, and if we double 0.01, that is 0.02. That means our p-value for the t-value of minus 2.2 with a two-sided t-test should lie between 0.05 and 0.02. That means it is less than 0.05. Actually, this should be the sign should be opposite way, I believe. Uh, but anyway, uh, these are the upper and lower bounds on the p-value, right? Actual p-value will be, if you calculate using computer, will be 0.042, and we will do that. So that's not a problem. So here are the computer to sample t-test results that are shown using some statistical software in our book, where we have uh, the first we have the basic information: mean, standard deviation, sample size for modified and unmodified formulation. Then we have the t value of minus 2.2, correct? The 95% confidence interval for the difference between mu1 and mu2 is also calculated, generated by the statistical software. P value is 0.042. This is a jump statistical software, okay? So we can do that using Excel. So let's try to do that. But before we do that, I just would like to quickly go over this slide here. The p-value is the area in the tails of the t distribution beyond minus 2.2 plus the probability beyond plus 2.2. It's a two-sided test. The p-value is a measure of how unusual the value of the test statistics is given that the null hypothesis is true. In other way, the p-value is the risk of wrongly rejecting the null hypothesis. And the smaller that risk is of wrongly rejecting, that means we can more and more confidently reject null hypothesis. Smaller and smaller p-value is, more and more confidently we can reject the null hypothesis of equal means. That means there are differences between the two samples, and less than 0.05 means we should definitely reject null hypothesis, right? With a 95% confidence. The exact p-value in our problem is p is equal to 0.042, which we will find out. But so let's perform the t-test using Excel. We just now we performed the t-test using the calculating the t0 value, then taking it to the t distribution tables, and from there calculating the p-value, and then making conclusion, right? But same thing can be easily done in Excel. So I have here a Excel file that I will open. Okay, and let's. Oh, I have already the data in the spreadsheet here. Let So let's perform the analysis. I'm gonna go to the data tab and data analysis and the t-test. We need to use the t-test to sample assuming equal variances. That is correct, not assuming unequal variances, because that's why we used the pooled sample variance, right? SP or SP square. So equal variances. Okay. Variable one range is the modified group. Variable two range is unmodified group. Hypothesize mean difference between the mu1 and mu2. If we don't put anything, it would be 0, and that's what. So I'm not gonna put 0 there. Uh, Leave it blank. It's default 0. In the selected data, do we have labels in the first row? Yes, right. alpha values of 0.05, that is also we always use that. And I'm going to put output somewhere here for us to look at. Okay, so let's see the results of t-test. So first of all, we are performing two-tailed t-test. So I'm going to hide the Excel gives us both one tail and so I'm going to hide this one tail results. So let's me go to view or home tab here and just blanken them out. Okay. So we got the mean of the two groups. We have the variance observations. We have the pooled variance 0.0808, and we can compare these values with values we have just for the analysis purpose. So here SP square is 0.081, right? uh, 0.081. There's some rounding off differences you will see, but if you round it to the three decimal places, 0.081. Degrees of freedom 18. We know that n1 plus n2 minus 2. The t statistics we calculated here minus 2.2 and very close minus 2.19. Or as I say, there will be always rounding off errors, but very accurate. And the p-value is 0.042. That's what we have. uh, let's see here, the computer value is p.042, right? So we got the that p-value, and since that p-value is less than 0.05 alpha value, we can reject the null hypothesis. I hope you understand the this part, right? P-value has to be less than 0.05. So that's how you perform t-test in Excel. Now let's continue the discussion. Next thing about the t-test is, next part is checking assumptions. Uh, we assume that the data that we collected on the tension bond strength in our problem, it's a tension bond strength for the two different formulation, that is the norm, that data is normally distributed. Uh, so we have to make a normal probability plot to show that the normality assumption, the normal probability assumption on the data is true, not violated. So how that test works? It's called thick pencil test. So you basically plot the data on the tension bond strength on x-axis and the percentage cumulative normal probability distribution on y-axis for modified and for unmodified. So you plot this data and then you have a normality line passing through it. And if the data is the data points is nicely along they travel along the line, that means the normality assumption is true on our data. That means and this assumption has if this assumption is verified, then our results of our t-test are reliable. If this assumption is not verified, or if this assumption is violated, let's say we have points here, points there, right? The points are not following across a nice normal line. That means there are some issues, there are some problems with the data collected from our experiments. Okay. And what happens in that case is not right now we will discuss, but our goal is to check the assumption. So can we make this plot in Excel? I think so. So let's go ahead and make this plot in Excel. So what I am going to do is, first of all, I think I need a couple of columns here. I need to push that t-test result further down. Okay. I need to sort both the data here for both groups. So I'm going to select these, right click, sort smallest to largest, expand the selection because it sees data in the next column. Say no, continue with the current selection, right? Okay, so that group is sorted. Then this group also should be sorted. Sort from smallest to largest. Once again, continue with the current selection. Okay, so we got both groups sorted. Then we create a column called sort order. Okay, and let's see, 1 2 3. So that is our sorting order, 1 to 10. Next, we need to if you look at the so we have the x-axis value strength. We need the percentage cumulative normal probability, right? So cumulative normal probability times 100 is the percent cumulative normal probability. So we need to do that. So percent cumulative normal probability, and formula for that is equal sort. So I start parenthesis, sort order minus 0.5, always, right? Sort order minus 0.5 parenthesis closed, divided by n, which is the sample size. Sample size is 10 in our case, so divided by 10. And we have to multiply that by 100 because we want to calculate in terms of percentage. So multiplied by 100, and then we can autofill this. So basically your cumulative probability should start from 0 and it goes all the way to 100%, right? 0% to 100%. So this is nicely 5%, 15, 25, looks good. Okay, now we need to plot them. So we go to insert. I will make a simple scatter plot here, blank scatter plot. Then we'll fill that, of course. So let's select data for this scatter plot, add series name, let's say modified. Okay, and we are going to select range of x values is those, and y values are the respective percent cumulative normal probability. And that's good, right? Then we need to add one more data series. This one is for unmodified. Series x values are those, and the y values are same percentage cumulative normal probability. And we got it here. So here is our chart. Let me make it full screen. Okay, so here we have this chart. Now uh, we can this is nicely from 0 to 100. uh, you can add the chart titles if you want. You can, for example, you can go to the format, or you can go to chart design and you can select quick layout, and you can add this axis title here, right? So here you can say percent cumulative normal probability. X-axis title is these are the tension bond strength values, right? Tension bond strength. And the chart title, this is the normal probability chart. Normal probability chart. And now we can add those lines. So I select this for a modified. I select the data and I right click on that those data points and I add trend line. Okay, and same thing I do for unmodified. I right click and I add trend line. So as you can see, the our points are nicely following along that straight line. If we put a very thick pencil on that line, all the points will be hiding under the pencil. So that is thick pencil test. It's because we don't have any outliers or points far away from the lines. We can say that the assumption on the normal probability of data is verified, right? Is uh, correct. So that's how you perform this analysis. Now let's go back to the presentation. So that's basically the t-test. You perform the t-test, you make the conclusion, you check the assumption of normal probability. So let's summarize the importance of t-test. T-test provides us an objective framework for simple comparative experiments, right? Uh, it doesn't matter whether our sample size is big, small. Also, we don't have to know the population variances as we need to know in z-test. It could be used to test all relevant hypotheses in a two-level factorial design. Whenever there are two groups, we need to compare two groups, we can confidently use t-test because all of these hypotheses involve the mean response at one side of the cube versus the mean response at the opposite side of the cube. We can also calculate confidence interval because hypothesis testing gives an objective statement. It says whether the null hypothesis should be rejected or not rejected, but it doesn't specify how different the means are. For that, we can use confidence interval. The general form is something like that. The There is a lower limit and upper limit. So the difference mu1 minus mu2 would be between those lower and upper limit. And the probability of that confidence interval is 1 minus alpha. Alpha we always use 0.05. So that's why they say, or we alpha is 5%, right? That's why they call it 95% confidence interval. 100 times 1 minus alpha, 1 minus 0.05. So 95% confidence interval on the differences in two means. And it's given by this formula. We can use this y1 bar minus y2 bar. We know the sample averages. We can take the difference minus t alpha by 2 at n1 plus n2 minus 2 degrees of freedom. This is not the calculated t value. This is the reference t value, right? At 0.025 times the sp times the square root of 1 over n1 plus 1 over n2. We know all of that. This mu1 minus mu2, the lower bound is this and the upper bound is this subtraction basically becomes addition here. So if you plug in all the values for our problem, the actual 95% confidence interval estimate for the difference in mean tension bond strength for the formulations of Portland cement mortar uh, can be found like this by plugging those values, respective values. So the difference between the two groups, the tension bond strength is lies between minus 0.55 and minus 0.01. And you will notice that 0 is not included in this interval. Both sides, this is negative, Upper lower bound is negative, upper bound is also not negative. Zero is not included, and that's true because there are significant. We already said the null hypothesis is not true. We rejected null hypothesis, which says mu1 is not equal to, which says mu1 is equal to mu2, and we rejected that. That means we are saying mu1 is not equal to mu2. If we see the zero in the parenthesis, the this confidence interval, that means null hypothesis is true. Mu1 is equal to mu2, and that's the only way we get zero in this confidence interval, right? Thus, the 95% confidence interval estimate on the difference in means extend from minus 0.55 to minus 0.01 kilogram force per square centimeter. Put another way, the confidence interval is minus 0.28 plus or minus 0.27 kilogram force per centimeter. Uh, and you can also calculate that using Minitab software and Jump software, but it's very easy calculation. You can do manually also. So that's where I will close this video. In next video, we will discuss what if the two variances are different for the two groups. Then what should we do? But anyways, I will close this video now. Thank you.